In this video, we are going to look at how a computer goes from binary, just to numbers, to displaying a photo of your dog, playing your favorite song, or streaming a movie in 4K. We'll trace that entire journey from the absolute basics of what a bit actually is, how the message you send to your friend gets converted to bits, and how images are encoded. Let's start at the very beginning, the bit. A bit is the smallest unit of information a computer can understand. It's either a 0 or a 1. That's it. On or off. True or false. In the physical hardware, it might be high voltage or low voltage, but conceptually, it's just binary. Two possible states. Now, 1 bit alone isn't very useful, right? With 1 bit, you can represent exactly two things, maybe yes or no. But here's where it gets interesting. When you start combining bits, the possibilities explode exponentially. 2 bits gives us 4 combinations. 00, 01, 10, and 11. 3 bits give you 8, 4 bits 16, etc. Every time you add one more bit, you double the number of possible values. 8 bits, which we call a byte, can represent 256 different values. The question is, how do we get from these abstract numbers to actual information? We need a system, a set of rules that says, this specific pattern of bits means this specific thing. Different types of information need different encoding systems. Let's start with the simplest one, text. When you type the letter A on your keyboard, your computer doesn't actually store the letter A. It stores the number 65. Why 65? Because of something called ASCII, the American Standard Code for Information Interchange. ASCII is basically a lookup table created back in the 1960s. It says that the number 65 represents uppercase A, 66 represents uppercase B, and so on. Lowercase letters start at 97. Numbers, punctuation marks, even the space character, all have assigned numbers. Since ASCII uses 7 bits per character, it can represent 128 different characters. That was fine for English, right? But what about other languages? What about emoji? That's where Unicode comes in. Unicode is a much more comprehensive system that can represent over 1 million different characters. It includes every language you can think of: Arabic, Chinese, Korean, mathematical symbols, musical notations, and even ancient scripts that nobody speaks anymore. The most common implementation of Unicode is UTF-8. UTF-8 uses a variable number of bytes per character. Simple English characters still take just 1 byte, but more complex characters may take 2, 3, or even 4 bytes. So when you send a text message, your phone is converting each character into its Unicode number, then converting those numbers into binary, and transmitting those bits. The receiving phone does the process in reverse. Keep in mind that this is just a simplified explanation. There are many steps that happen to deliver that simple message. But text is straightforward since each character is just a number. Images are where things get really interesting. Let's think about what an image actually is. If you zoom in far enough on any digital image, you will see it's made up of tiny squares called pixels, and each pixel has a color. So, the simplest way to store an image is just to record the color of every single pixel, one by one, from left to right, top to bottom. But how do you encode a color as a number? Red, green, blue. The idea is that any color you can see on a screen can be created by mixing these 3 primary colors of light in different intensities. In a typical RGB system, each color channel gets 1 byte, so 256 possible values, from 0 to 255. 0 means none of that color, 255 means maximum intensity. Pure red will be red, obviously. Set at 255, green set to 0, and blue 0. Pure white is all 3 at maximum, that is 255, 255, 255, and black is all zeros, that's 000. That means each pixel takes 3 bytes of information. Now, multiply that by every pixel in the image. A standard high resolution, 1920 by 1080 image, has over 2 million pixels. 3 bytes per pixel, that's about 6 megabytes of data for a single image. And this is for a simple format called bitmap, or BMP, where we just store every pixel exactly as it is. This is massively inefficient, which is why we almost never actually save images this way. Instead, we use compression, and this is where things get clever. There are 2 types of compression, lossless and lossy. Lossless compression makes files smaller, without losing any information. PNG files use lossless compression. They look for patterns in the data, like if you have 10 pixels in a row that are all the same color. Instead of storing that color 10 times, you just do it once and say, repeat this 10 times. Lossy compression is where we really save space. JPEG files use lossy compression. They intentionally throw away information that your eye probably won't notice is missing. JPEGs work by breaking the image into 8 by 8 pixel blocks and converting the color information into frequency information, how quickly colors are changing. Then it throws away the high frequency details that you are less likely to notice. The more compression you apply, the more detail you lose, which is why heavily compressed JPEGs look blocky and weird. This is why a photograph might be 8 megabytes as a PNG, but only 2 megabytes as a JPEG. We are literally throwing away 75% of the data, but if it's done well, you barely notice. That's it. I hope you learned something new and this video was informative. Thanks for watching.